Hi, everyone. Thanks for joining us. I'm Nick Erickson, your host for this webinar. Today, I'm joined by Ian McEnteggart, the Composites Market Manager at Instron. Ian has worked in the materials testing world for over 40 years, in which time he's been somewhat of a double major, you could say, with his first passion being composites testing, followed closely by metals and other alloys. He's also chair of the UK Composites Standard Committee and a member of various ISO committees that develop the testing standards that many of you may be using in your labs every day. In this webinar, Ian will be providing an introduction to testing machine alignment, why it's important to testing metals and composites, and he'll also share some insight into how you can make sure your testing machine is well aligned and can meet stringent ISO and NADCAP standards. We're also joined by Stefan Botsky, one of our high force application engineers. Stefan will be keeping an eye on any questions that come in while Ian is presenting, so I encourage you to send those in as we go along. Don't feel like you need to wait until the end to send in any questions you might have. Stefan may respond to some of those as we go. With that said, I'm going to turn things over to Ian.
Okay, thanks very much, Nick, and hello to everyone who's listening in. Myself, Stefan, and Nick will be doing this webinar today. Okay, so we're going to cover what is alignment, what do we mean by alignment, why is it important, methods of achieving and maintaining good alignment, gripping as well as machine alignment. How do you measure alignment? How do you quantify alignment? What are the relevant alignment standards? And I believe we're going to have time for some questions. We have a few questions that have been filed already, so we'll pick those up at the end. Okay. So what do we mean by alignment? Well, in the center of this slide here, you've got typical testing machine load string, load cell grips, hydraulic grips in this case. And we got a couple of cases where you can clearly see they're not perfectly aligned, right? They're not completely coaxial. And we're quantifying this in two ways. We mainly talk about angularity errors, which this is a case of angularity on the left-hand side. And you can see, obviously, it is causing curvature in the specimen. So we've got an increase in the positive tensile strain on one side. We've got a compressive strain on the other side. And of course, these strains would be summed with the overall axial strain. So, but they're going to result in a non-uniform strain distribution across the specimen. In the other case, we might have the grips might be parallel. I mean, these are extreme cases, but they might be parallel, but they might be offset. So we've got a concentricity error here. And you can see again, and this would create some kind of S-type bending in the specimen, which is probably worse than the sort of gradual bending because of the curvature is larger for a given size of specimen. And obviously, the whole thing kind of relates to the specimen size, because if you have a long specimen, these effects are going to be less. If you've got a short specimen, they're going to be greater. So tend to talk about standards, tend to talk about specimen alignment. As a machine manufacturer, we tend to talk about machine alignment, and it's important to get those two things kind of coming together. So why is it important? Well, obviously, if we're not achieving a uniform strain in the uniform stress state in the specimen, we're going to have higher stress areas, lower stress areas. We're going to get yielding in part of the specimen that's under the higher stress. If it gets a metals test, we get an uneven stress distribution, we get misalignment. It's going to influence the modulus and the yield results here. We had an extensometer on this side of the specimen, it's going to read less strain than on this side, and on the other hand, the axial stress is going to be more or less the average stress. So it will influence the modulus results. It's going to give us an incorrect yield result as well. The stress distribution means that once we're into the plastic area of plastic deformation, we're probably not going to be too much of an influence of misalignment on that part of the curve, but it's generally the first part of the curve that we're really interested in anyway, and so that's going to be influenced. On the other hand, if we're testing composites are particularly sensitive to misalignment because they're generally fairly brittle materials, so about resin-based, thermoset resin-based composites used in aerospace. They're pretty brittle. The fibers will start to break in the high stress areas, and once the first fiber breaks, then you're going to get a fairly rapid failure of the whole specimen. So that's going to influence the UTS and the ultimate stress and strain results. So not a good thing. And there's so like I say, in getting inconsistent results with this alignment, we're getting tending to be lower results. So we're underestimating the material's performance. In some areas, like particularly aerospace, they're working on the regulatory framework, which would include NADCAP type checklists and requirements. So you can see that in general for the metals testing, NADCAP are defining 10% bending strain for ductile materials, 8% for non-ductile, 5% for cyclic fatigue type work. And again, in composites area, we're looking at say an 8% limit on bending strain. And we did an exercise a few years ago in Instron where we actually deliberately introduced misalignment into some composite specimens, and we got comparative data for where we have some poor alignment, and when we went to good alignment, you can see reduction in scatter and the increase in the properties. And that's something that is available as a white paper. You can download it from our website. I think it'll be available as part of this talk. So let's go on and look at how we achieve good alignment on testing machines. So basically, there are essentially two approaches here, sort of complementary approaches. There's a self-aligning approach where we deliberately introduce or deliberately include flexible couplings into a load string. You see the flexible couplings here on either end of this high temperature load string on this machine. And we also, and this is very suitable for round specimens, but they need to have threaded or button ends because those specimens need to be coaxial with the center of rotation of the flexible couplings in order for this thing to self-align correctly. It is a common approach for high temperature metals testing. There you see a high temperature furnace on this system, long rods into the furnace and these flexible couplings, and this is great for tension, completely inappropriate for compression. When we're looking at a load string for both tension and compression, and we're also looking for use with both flat and round specimens, particularly say composite laminate specimens, we really need a rigid approach, a rigid load string. So this is an example of a rigid load string here, and in this case for operation inside a temperature chamber, but it could be for operation at room temperature. And this load string, it will achieve good alignment in tension and compression, and it will support the ability to what we call piggyback, or to mount other composite testing accessories, other accessories in between the main grips. So that's some of the advantages of that approach. So if we look at the self-aligning load string in a little bit more detail here, here's a couple of examples. Here's a room temperature example on a small static hydraulic system. This approach It's not particularly dependent on the characteristics of the testing machine, since you're allowing the string to self-align. So in this case, the universal joints have spherical joints here, and this is the detail of the spherical joint. This would be up at the top of the machine here, and there'd be a similar one at the bottom. The specimen itself needs to be located accurately, as we said earlier. So usually this means you need a threaded specimen or a button-ended specimen, and of course that's a common specimen design for high temperature use. So we go to rigid load strings. So the first thing about when we're using rigid load strings is we need a precision built guided testing machine with high axial and lateral stiffness, because it's no good having a rigid load string in a machine that is itself not rigid. In this case, you can see a machine, electromechanical machine with large diameter ball screws, with guidance columns inside these covers here. So very nice, stiff, big stiff crosshead, nice big stiff load cell as well. So kind of testing characteristics of the testing machine that we require, and then we can then augment that with an alignment fixture, which mounts between the crosshead and the load cell. So here we see this would be sitting here. This is the alignment fixture, and this is really a vernier adjustment for angularity and concentricity. So it gives us very fine control over the angularity and concentricity on the machine, and we can use it to adjust the load string until the alignment is very good. And that integrates with the measurement system as well. So we'll talk about that in a few slides. It's no good having a very stiff, well-aligned load string if the grips are not repeatable. We need very repeatable grips. So the characteristics of the grips that are required, typically, we would always recommend a moving body grip. So here's an animated example of a moving body hydraulic grip. The picture, this is a moving body manual grip. So these characteristics can be applied to either hydraulically, automatically operated, or manually operated grips. We need some kind of so the moving body means that the faces move horizontally. So if you look at this, the faces are not moving vertically relative to the specimen. So they're closing on the specimen in a very controlled way. That's not the case. That wouldn't be the case with a moving jaw grip, where the grips are pushed onto the specimen vertically. So you've got that double motion, because that's not a repeatable action. This is. The other thing is the symmetrical wedge pocket controls the alignment of the jaw face. This is totally well guided and symmetrical. So these jaw faces are always looking to meet on the center line of the testing machine. And then also the symmetry of the body extends to the front back direction, because we want to maintain and be able to validate alignment under load. And under load, obviously everything moves to a certain extent, so there will be some elastic deformation in the grip body, and if that is not symmetrical, for instance, if we had a closed back to this grip, then that grip could introduce some bending under load. Finally, we need to be able to insert the specimen in the grips in an accurate and repeatable fashion. So we need specimen stops, a couple of examples of specimen stops on grips here that will ensure that we have specimen stops on both grips, of course, so ensure that we don't have specimens misaligned like you see at the top here. And then for compression alignment, there are grips, they're hydraulic wedge grips, typically moving body hydraulic wedge grips like we were just talking about. can be used to load specimens in compression via shear loading, and in a machine with high lateral stiffness, and to maintain the alignment under load. That's perfectly possible. Often the compression testing is being done between compression platens, and in that case it's important to have the ability to align the compression platen, in this case usually performed by having a compression platen with a spherical seat. So we have a pair of compression platens, one with a spherical seat, one fixed. They can be driven together and then locked up once they are perfectly parallel, and that kind of thing will meet the requirements that NADCAP state for compression accuracy of platens. Then there's a whole raft of composite fixtures, particularly for compression, which actually integrate guidance and alignment into the fixture. So one example would be the this ASTM D6641 combined loading compression jig, which you see a picture of it here and a diagram showing the bearings, and obviously this is laterally stiff and well guided. So this would simply be used between sets of compression platens on a machine, but the guidance is actually coming from the fixture rather than the machine in this case. So that's talking about that's how we could achieve alignment, maintain alignment. But how do we measure alignment? Well, measuring alignment is performed using strain gauge specimens. So we call it strain gauge specimen or strain gauge alignment cell sometimes. These are generally, we try to be representative of the test pieces or the test samples that are being tested. In which case, so they should be designed to operate at the lowest force level. But if you're testing metals, it would be the yield strength of the smallest specimen, or its weakest specimen. You try to maintain similar form and dimensions as the test specimens, so that the gripping arrangement is obviously consistent. The materials, the practice is to use either steel or titanium. These materials hard steel have excellent elastic properties, because we need something that is not going to yield within the range of use, within the forces that we're looking at. So it needs to be in quite a hard state, so we don't get any yield behavior, no plastic deformation. These things are acting as essentially miniature load cells. And the specimens have sets of gauges. In this case, we have two sets of gauges, so a total of 8 gauges, 4 gauge top, 4 gauges bottom. The 4 gauges gives us the ability to compute the bending strain and the direction of the bending strain. There are other geometries used, ISO 527 parts 4 and 5, specify alignment cells which just have 3 gauges, but that's rather limited in terms of what it can do. NADCAP specify a 12 gauge flat specimen, which is used for composite checking testing on composite systems, and that's made out of steel. Composites themselves don't make good materials for these cells. Made out of steel, and that's 12 gauges. So again, it can determine the bending and the direction of the bending, because we have pairs of gauges, 6 on one side, 6 on the other side. And finally, from a practical point of view, strain gauges are fragile devices. They need protection. We have a range of standard alignment specimens where we put an aluminium protection sleeve on here, a cylinder here to protect the gauges, and have strain relief on the cable connections so that these things don't get damaged. If your other techniques are just to put protective lacquer over the gauges, but that's not quite as good, not as permanent. So having got the signals from the strain gauges from our alignment cell, our Align Pro system will process the gauges. We can process up to 12 gauges with the electronics. Then the signals are sent to a PC set of software, Align Pro software, which then computes the magnitude and the direction of the bending strains. It also splits it into both a concentricity component and an angularity component, and that's important in trying to understand where your alignment is sitting if you're going to make some adjustments to it. So here's slightly blown up view of the screen, and as you see, we've got both the concentricity here in orange and the angularity in blue. We've got the magnitudes, and in this polar display, we've got the magnitudes, and you've got the direction, and you've got numerical values here with the average strain from the gauges, the bending strains, and next you'll see you've got the ability to. It's suggesting how you would actually improve the alignment. So the software is calculating what needs to be done to improve the alignment. And there we can see just the concentricity, the angularity is turned off. So this is the process. We have the Align Pro system. We have a strain gauge specimen. We are looking at the results, looking at the bending strains here on this screen, which is a real-time screen. It's being updated all the time, and it is giving the guy who's setting up the machine is giving him instructions as to how to adjust the fixture for adjusting the angularity and the concentricity. All this is being done while the system is under load, and obviously once we've made the adjustments, we're continually monitoring those results so we can see what's happening. We can also produce certificates from this system, and indeed our service organization has the ability to perform fully accredited alignment calibrations, and they would produce the certificates using this type of software. Standards wise, the main popular standard or most common standard for the alignment verification is the ASTM E1012, which was updated last year. It contains detailed procedures on how specimens should be produced. It includes classifications, includes classifications at 5%, 8%, and 10% bending strain. There is also an ISO standard, less commonly used. It is titled fatigue testing machines, but could be used for monotonic testing situations as well. There's a NADCAP standard, the NADCAP checklist for materials testing labs, mechanical testing, which again has classes of 10%, 10% for static tests, 5% for cyclic tests. That's mainly for metallic testing. The non-metallic materials, which is mainly composite materials, AC 7122, again defines specimen designs like the 12 gauge specimen we were looking at earlier, defines bending strains of 8% and 5% for composite testing, static and cyclic type testing. So I guess to sum up, I would like to say that alignment is not a relatively complicated area. There's a lot of variables in this area, and we would, as a supplier of testing machines, we are always happy to actually commit to levels of alignment on complex systems like the one you see here. So we would guarantee particular level of alignment on a system like this, happy to take that on as a contract. We have the service organization to actually validate that performance. So we are, from the point of view of an end user, it's a de-risking process. So that really concludes the main part of the presentation, and we'll move on to questions.
Yeah, thank you very much, Ian. That was great. And yeah, we have some questions that came through. The first one is, can I change parts of my load string, for example, the jaw faces or even the grips?
Yeah, the specifically, I think within NADCAP, you are allowed to change jaw faces without rechecking the load string. But if you were to change a major part of the load string, or you were to suspect there'd been any any damage that might have affected the alignment, then the advice is to recheck the alignment at that point.
Thank you. I think that makes sense. Next question was, what are some best practices for overcoming slack in the alignment caused by thread engagement of load train components?
Okay, well, I think in this area, probably the key thing is preloading, and actually having if you're looking at threads, you need a lock nut to be able to get rid of the backlash or the deadband in the thread, and generally you'd be looking at pulling your load string up to its maximum load, and then nipping up the lock nuts, and then releasing the load, and that should remove any slack due to slop in threads. I mean, the other way of doing it is to run your test after a preload. So, but that's not really quite as good as actually getting rid of the slop by preloading everything once and for all.
Thank you. I think that answers it. How often should I have the alignment checked on my system?
Okay, well, I mean, this is the kind of thing that would be written into a quality system. I mean, it's generally, I think we're looking at sort of an annual kind of check, unless, again, as we said earlier, unless load strings are being changed, configurations, you're going for different configurations, in which case you should check it every time something is changed. But generally, once a year, similar periods to the load verification on a machine.
Great, thank you. Okay, you talked about hydraulic and mechanical grips. One question was, what is the difference between mechanical and hydraulic grips in terms of alignment?
Okay, well, there really isn't. There isn't a fundamental difference. I mean, the two grip examples that I showed were both a moving body grip, and that's the key. That's really the key principle. Having a moving body, well guided, accurately guided moving body. Now, whether you move that body with a hydraulic piston, or you move it with with a mechanical gear type mechanism, really you're going to get the same result as regards alignment. So I would say, there isn't a fundamental difference.
Thank you, that makes perfect sense. And then maybe the last question that we have time for. At what force level should I check the alignment of my testing machine?
Okay, well, this goes back. I mean, there are different bits of advice, but I think the general advice would be that you would take your lowest, you take the yield point of your sort of weakest material, smallest specimen, weakest material, the yield point of that, which would give, that would be the lowest load that you would be reporting results at. and you'd take that load and you'd verify your alignment at that load, and probably some loads above that. But in general, it's going to be the low load is going to be the critical one. So you cover that, you validate that, and everything else is going to be lower bending anyway. But you probably want to try and cover that. So yeah.
Great, thank you. And in case we didn't get to answer your question, we'll try to follow up on them. And yeah, thanks. And back to you, Nick.
All right, thanks, Stefan. That is going to do it for today. Before we wrap things up, I do have one quick note. We will be posting today's recording on our YouTube channel and also be emailing each of you a link to that recording plus Ian's slide deck. But if you haven't already seen it, we do have a handout section where you can download the white paper that Ian mentioned earlier, along with the slide deck that you saw today, and the high force universal testing machine brochure that highlights a lot of the machines that you saw in those images from Ian's slide deck. I do see some other questions kind of coming in as I'm wrapping up here. I think Stefan and Matt are working on getting answers to those. Otherwise, we will follow up with those people that did ask questions by email. So with that said, I just want to thank Ian for joining us today. And Stefan, thanks so much for being here to keep an eye on questions. Matt as well. And thank you all for attending. Stay healthy, everyone. We hope to see you again at a future webinar.